Let's look at solutions and their properties. First, we define a solution. A solution is defined as a mixture of two or more substances distributed throughout a single phase. Okay, so a solution is made up of a solute and a solvent. Okay, so solution is equal to solute plus solvent. A solute is a substance being dissolved, e.g. sugar. Okay, then a solvent is a dissolving medium, e.g. water. Okay, so sugar plus water is equal to sugar solution. Okay, so sugar solution forms now a single phase. Okay, so solute plus water, solute plus solvent, water, forms a sugar solution. Okay, so solutions, we have various types of solutions. So a solution can be a gas, can be a liquid, or a solid. Okay, so let's look at various types of solutions. Example: state of solution, state of solute, then state of solvent. For example, air or natural gas. State of solution, gas. State of solute, gas. State of solvent, gas. Okay, then we can look at antifreeze. Okay, this is used as coolant in cars radiators. Okay, this one is a liquid. State of solvent, liquid. Okay, brass is an alloy of zinc and copper. Okay, so it's a solid. Okay, can also look at carbonated water. So here carbon dioxide dissolved in water, carbonated water. Okay, like carbonated drinks. Okay, state of solution, liquid. State of solute, gas, which is carbon dioxide. State of solvent, that's a liquid. Okay, then seawater. So we have seawater, we know there's salt. Okay, so we know that the solute is salt. Then state of solution, liquid. State of solvent, liquid. Okay, then hydrogen in platinum. Hydrogen is a gas. Okay, this one is a solid. Platinum is a solid. Okay, so these are the various types of solutions. Okay, so you can see clearly here that a solution is not only a liquid, it can be a gas, liquid, or solid. Okay, then solutions are classified as saturated, unsaturated, unsaturated, and supersaturated. Okay, so we start with the saturated. Okay, so let's define saturated solution. Saturated solution. Okay, so a saturated dissolution is formed when no more solute will dissolve in the solvent. Okay, that's a saturated solution formed when normal solute will dissolve in the solvent. Okay, the second one, unsaturated. Unsaturated solution is formed when it can still dissolve. Is formed when it can still dissolve more solute. That's the unsaturated. Okay, then supersaturated solution, okay, is formed when you put solute in the solvent in excess. Is formed when you put solute in the solvent in excess. Okay, so it means the solvent will not be able to absorb the whole solute. Okay, so in this case, to make it dissolve, you need to increase the temperature. Okay, so once you heat the solution, we know that most salts are soluble. Most salts are soluble in hot water than cold. Okay, than cold. All right, so now let's look at the effect of okay, before we get into the calculations, maybe first of all we need to look at solution content. Okay, so let's look at various ways of expressing solution composition, okay, or concentration. So let's look at solution composition. Okay, so we want to look at various ways in which we can express our concentration. Okay, so the relative amounts of substances must be specified. Okay, so we encounter terms as dilute. Okay, dilute solution. Okay, so dilute simply means there's relatively to solute. Okay, that's the dilute. Okay, relatively little solute present. Then concentrated means relatively large amount of solute. Okay, so for example, when you make a cup of coffee, So suppose this is A, B. Okay. So here you add, this is coffee. Okay. Coffee. So in cup A, you add 1 tablespoon of sugar. Okay. So here 1 tablespoon of sugar. Then here you add 3 tablespoons. 3 tablespoons of sugar. Which one do you think is more concentrated? So this one is dilute. A is dilute, then B is concentrated. Okay, so that's the difference. Okay, so the more solute present, the more concentrated the solution will be. Okay, so let's look at concentration of solution. Concentration of solution. Okay, so concentration is a measure of the amount of solute in a given amount of solvent or solution. Okay, measure is a measure of the amount of solute. Measure of the amount of solute in a given solvent, in a given amount of solvent or solution. Okay, measure of the amount of solute. So we are going to measure the amount of solute present in a solvent or solution. So measure of the amount of solute in a solvent or solution. Okay, so other than we all know that molarity M is a common measure of concentration that we know. Okay, so molarity is equal to moles of solute over liter solution. That is molarity. Okay, molar. So the volume, moles of solute over volume of solution. So there are also other ways. Other than molarity that we are going to look at. Okay, so we can measure concentration by mass percent, weight by weight, or mass by mass. Okay, so in chemistry, weight and mass can be used interchangeably. Okay, so mass by mass. Okay, so in chemistry, when you say what weight, we mean mass. The two terms can be used interchangeably. Okay, so mass percent is equal to mass of solute over mass of solution times 100%. That is how we shall be calculating mass percent. Mass percent is equal to mass of solute over mass of solution times 100. Okay, so we also have molality. Okay, molality. So molality is equal to moles of solute over kilograms of solvent. That is molality. Okay, So the units will be mole per kg. Mole per kg. Okay, that is molality. So mole per kg is equal to mole, which is equal to m, small letter m. We all know that with molarity, it is capital M, molar. So this one is molar, small letter m. Okay. So we also have mole fraction. Mole fraction, which is denoted by the Greek letter chi. Okay. So mole fraction of component A. Mole fraction of component A. Mole fraction of component A. So we say chi A is equal to moles of A over moles of A plus moles of B. That is the mole fraction. Okay. Then, where n is number of moles. N is number of moles. Okay. So mole fraction of solute. Mole fraction of solute plus mole fraction of solvent is equal to 1. Mole fraction of solute plus mole fraction of solvent is equal to 1. Okay, so it means that mole fraction can never be greater than 1. Okay, that's the total it can ever achieve 1. Okay, so that's the formula. Okay, so if we want to calculate mole fraction of solvent or solute, so mole fraction of solute is equal to moles of solute over moles of solute plus moles of solvent. That is mole fraction of solute. Then mole fraction of solvent is equal to moles of solvent over moles of solvent plus moles of solute okay, plus moles of solute. That is mole fraction. Okay, then we can also express concentration in terms of ppm and ppb. Okay, so ppm means parts per million. Then ppb, parts per billion. Okay, so ppm by weight or mass by mass, or ppm by mass or weight by weight. Okay, so ppm is equal to mass of solute in grams over mass of sample in grams times 10 to the power 6. That is ppm, weight by weight or mass by mass. Okay, then ppb, mass by mass, is equal to mass of solute in grams over mass of sample in grams times 10 to the power 9. Okay, so if it is weight by volume or mass by volume, then mass of sample now becomes mass of solution. Here also mass of solution. Okay, so we can also calculate ppm by simply dividing microgram per gram. Okay, that is ppm. Microgram per gram, it will give you ppm. So ppm is also equal to microgram per gram or milligram per kg. That is also equal to ppm. Then ppb is equal to microgram per kg or nanogram per gram. Okay, so these are the other ways in which you can calculate ppm and ppb apart from using the formula. Okay, so that is how we can calculate. Okay, so now we can have an example. Let's see how we can calculate using various types of concentration content. Okay, so we are going to express concentration in various specifications. Okay, so a solution example, a solution is prepared. A solution is prepared by mixing 1.00 grams of ethanol. 1.00 grams of ethanol, C2H5OH, ethanol. Okay, 1 gram of ethanol with 100 grams of water, 100 grams of water to give a final volume. To give a final volume of 101 milliliter. Okay, so calculate a molarity. Okay, then B mole fraction, I mean in mass percent. So let's start with the mass percent. C mole fraction. Okay, mole fraction, and molality, and D molality of ethanol. Okay, solution. So we start with the molarity, the one we all know, the popular one. Okay, so molarity is equal to moles of solute over liter solution. Moles of solute over liter solution. So in this case, ethanol and water, you need to identify the solute. But water is never a solute. Okay, water is always a solvent. So a solute in this case is ethanol. Okay, so you need to calculate the moles of ethanol. So let's calculate moles of ethanol. Okay, so moles of ethanol, we know moles is equal to mass over molar mass. So the mass of ethanol is 1 gram. Okay, 1.00 gram. Then molar mass, the molar mass of ethanol is 46.07. 46.07 grams per mole. Then you divide 1 over 46.107. It is giving us 2.17 times 10 to the power negative 3 times 10 to the power negative 2 times 10 to the power negative 2 moles. Negative 2 moles of ethanol. Okay, so these are the moles of ethanol. Okay, then now molarity of ethanol is equal to moles of ethanol 2.17 times 10 to the power negative 2 moles over volume. The volume of the solution, is 101. Okay, 101. So we convert volume into liters. Okay, so 101 times 10 to the power negative 3 liters. Then now you divide. Okay, so you are going to find 0.215 moles per liter, or simply 0.215 molar. Okay, so that is the molarity. Then mass percent. So this is our A. Then B, let's calculate mass percent. So we know mass percent is equal to mass of solute over mass of solution times 100. Okay, so in this case, mass of solute, that is 1 gram. Okay, then mass of solution, we know that solution is equal to solute plus solvent, so you add solute, then mass of solvent, which is water, 100 grams. Okay, so you add the two and divide. Okay, so we are going to find 0.990% ethanol. Okay, so that is the mass percent. Okay, mass of solute over mass of solution. Then let's calculate the mole fraction. The mole fraction of ethanol. The mole fraction of ethanol. Mole fraction of ethanol. Okay, so mole fraction of ethanol is equal to moles of ethanol over moles of ethanol plus moles of water Okay, so we need to calculate moles of water. Okay, so moles of water is equal to, so we know that the mass of water, the mass of water is 100. Okay, so 100 grams over 18.02 grams per mole, so which is giving us 5.56 moles of water. 5.56 moles of water. Okay, then we bring it here. Moles of ethanol we have already calculated, which is 2.17 times 10 to the power negative 2 moles. Then over 2.17 times 10 to the power negative 2 moles. Then plus moles of water, 5.56 moles. Okay, so you add down, then you divide. So when you do the arithmetic, you are going to find 0.00389. This is the mole fraction. So you can clearly see that the mole fraction is less than 0. Okay, then finally we find the molarity. Let's find the molarity. m. Okay, so molality is equal to moles of solute over kg solvent, kilograms of solvent. Okay, so in this case, the moles of solute, that is the ethanol, which is equal to 2.17 times 10 to the power negative 2 moles. Okay, then over kilograms of solvent, the mass of water is 100, then we convert it into kilograms. So 100 times 10 to the power negative 3 kgs. Okay, then now we divide. So when we divide, we are going to find 0.217. Okay, 0.217 more per kg. Okay, that is our molality, or you can simply say 0.217 mole with a small letter m. Okay, so that is how we can calculate, we can express concentration in various concentration terms. Okay, of course there are also other concentration terms that we can use. Okay, so meantime we can just look at this. Okay, so now let's look at the energies of solution, the energies of solution formation, the energies of solution formation. Okay, so formation of liquid solution takes place in 3 distinct steps. Formation of liquid solution takes place in 3 distinct steps. Okay, so we have step 1. Okay, so step 1 is the separation of solute. Separation of solute into individual components. Okay, so this is our delta H1 endothermic. The process is endothermic. The process is endothermic for delta H1. That is enthalpy of formation here. That's endothermic. Okay, the process is endothermic. Heat is being absorbed. Then the second step is overcoming intermolecular forces. Overcoming intermolecular forces in the solvent. Overcoming intermolecular forces in the solvent to make room for solute. Okay, to make room for solute. So delta H2 endothermic. The process is also endothermic for step 2. Okay, then step 3 now is allowing the solute, allowing the solute and the solvent to interact. Allowing the solute and the solvent to interact to form a solution. So that is our delta H3. the process is now exothermic. Okay, heat is being released. Okay, so the enthalpy of solution, the enthalpy of solution, the enthalpy of solution, the enthalpy of solution, delta H solution, delta H solution is equal to enthalpy of solution, delta H solution is equal to delta H1 plus delta H2 plus delta H3. Okay, so it's a summation. So we add, it's a sum of the individual enthalpies. Okay, so that is the enthalpy of solution. You add delta H1, delta H2, and delta H3. Okay, so now if the enthalpy of solution, if the enthalpy of solution is negative, if the enthalpy of solution is negative, if the enthalpy of solution is negative, it means the reaction is exothermic. Exothermic. The reaction is exothermic. So, and solution forms. And solution forms. Okay. If enthalpy of solution, if enthalpy of solution is positive, means it's endothermic, no solution forms. No solution forms. So solution will only form when the enthalpy of solution is negative. Okay, so we can look at a table or examples. Sometimes we can mix a polar solvent and a non-polar solvent. Okay, and what happens is the solution going to form. Okay, so mixing, okay, mixing polar. So if we have a polar solute plus polar solvent, polar solute plus polar solvent solution. Okay, so here solution forms. Okay, so polar solute plus polar solvent solution forms. Okay, so what of non-polar solute? Non-polar solute plus polar solvent. So here no solution forms. No solution forms. Okay, then what of non-polar solute plus non-polar solvent. Okay, so here solution forms. Okay, then polar solvent, polar solute plus non-polar solvent. So here no solution forms. Okay, so always remember like dissolves dissolves like. Okay, like dissolves like. Okay, so polar, it forms a solution. Non-polar, a solution is formed. Okay, so we can now look at, let's look at gas solutions. Gas solutions. Okay. Gas solutions. So we want to see some factors. So temperature. What are some of the factors affecting the solubility? So we have temperature and pressure. Temperature and pressure. Okay. So temperature affects the solubility of gases. So the higher the temperature, the lesser the solubility of a gas. Okay, so you can see that temperature is inversely proportional to solubility. Okay, then pressure has little effect on the solubilities of solids or liquids. Okay, so significantly increase the solubility of a gas. Okay, so solubility pressure, the pressure affects more of the solubility of a gas than that of a solid and liquid. Okay, so we are now going to look at pressure and gas solubility. Pressure and gas solubility. Pressure and gas solubility. Pressure and gas solubility. So the relationship between gas pressure and the concentration of dissolved gas is given by Henry's law. So the relationship between gas pressure and the concentration of the dissolved gas. Dissolved gas is given by Henry's law. Henry's law. Okay, so we look at Henry's law. So Henry's law is given by the equation: concentration of the gas is equal to K times P gas. Okay, or simply C times C is equal to KP. C is equal to KP. So where C is the concentration, C is the concentration of the dissolved gas. Concentration of the dissolved gas. C is the concentration of the dissolved gas. Okay, then K is Henry's law constant. Henry's law constant or constant characteristic of a particular solution. Then P is a partial pressure. P is a partial pressure. P is a partial pressure. P is a partial pressure of the gaseous solute. P is a partial pressure of the gaseous solute. P is a partial pressure of the gaseous solute above the solution. Gaseous solute above the solution. Okay, so that is Henry's law. Henry's law. Okay, so it states that the partial pressure of the gas is directly proportional to the concentration. Okay, pressure direct proportional to the concentration. Okay, so we can calculate the solubility. We can calculate the solubility. We can calculate the solubility of a gas at a new temperature using Henry's law. We can calculate the solubility of a gas at a new temperature, at a new pressure using Henry's law. Okay, so the formula is given as the new solubility is equal to solubility times the new pressure, solubility times new pressure over odd pressure. Okay, so if the pressure changes, we can as well calculate the solubility, new solubility. So let's have an example. Let's see how we can calculate the new solubility. Okay, example. What is the solubility? What is the solubility of oxygen? Gas? What is the solubility of oxygen gas at 25 degrees Celsius? At 25 degrees Celsius, and a partial pressure of 1150 atm, atmospheres, 1150 atm. I mean, let's use torr. Okay, torr. Okay, torr. If the solubility of oxygen, if the solubility of oxygen is 0.00414 grams per 100 milliliter at 25 degrees Celsius, and 760 torr. Okay, so this is the question. What is the solubility of oxygen gas at 25 degrees Celsius and a pressure of 1150 torr if the solubility of oxygen is 0.00414 grams per 100 milliliter, 25 degrees and 760 torr. Solution: new solubility is equal to solubility times new pressure over odd pressure. Okay, so we substitute The solubility given, it's there, which is equal to 0.00414 grams per 100 milliliter, then times new pressure. Our new pressure, that is 1150, okay, 1150 torr, okay, over odd pressure, that is 760 torr. So you can see that the torr cancels. Then you do your arithmetic. We are going to find the new solubility at 0.00626 grams per 100 milliliter. Okay, so that is how we can calculate to find the new solubility. So let's have another example on Henry's law. A soft drink is bottled. A soft drink is bottled so that at 25 degrees Celsius, contains carbon dioxide, contains CO2, contains carbon dioxide gas at a pressure of 5.0 atm. 5.0 atm. Okay, that's a pressure. Okay, over the liquid, 5.0 atm over the liquid, assuming the partial pressure of carbon dioxide, assuming the partial pressure of CO2, assuming the partial pressure of carbon dioxide in the atmosphere, is 4.0 times 10 to the power negative 4 atm. Okay, so calculate the equilibrium. Concentrations. Calculate the equilibrium concentrations of carbon dioxide in the soda. Both before and after. The bottle is opened. Okay, after the bottle is opened. Okay, then Henry's law constant for carbon dioxide is equal to 3.1 times 10 to the power negative 2 mole per liter atmosphere. Okay, so this is the question. A soft drink is bottled so that at 25 degrees Celsius contains carbon dioxide gas at a pressure of 5.0 atm over the liquid. Assuming the partial pressure of carbon dioxide in the atmosphere is 4.0 times 10 to the power negative 4 atm. Calculate the equilibrium concentrations of carbon dioxide in the soda both before and after the bottle is opened. So this is Henry's law constant. Solution. So the first one is before the bottle is opened. Okay, so we know that C is equal to, so concentration of carbon dioxide is equal to K times P. Okay, Henry's law is equal to Kp. Okay, concentration of carbon dioxide is equal to K of carbon dioxide, Henry's law constant for carbon dioxide, times the partial pressure of carbon dioxide. So before it is opened, it means before it has been exposed to the atmosphere. Okay, so we are calculating now the concentration of carbon dioxide in the bottle before it is opened. So K is equal to 4.0 times 10 to the power negative 4 atm. Okay, the K, that is atmospheric pressure. Okay, so Henry's law constant, which is 3.1 times 10 to the power negative 2 mole per liter atmosphere. Okay, then the partial pressure of carbon dioxide in the bottle is 5.0 atm. Okay, so you cancel the atm, then you multiply. You are going to find 0.16. So the concentration is 0.16 mole per liter. Okay, then now we calculate after the bottle is opened. Okay, so what we mean that by that, after you opened the bottle, it means now the pressure will be equal to the atmospheric pressure, since it has now been exposed to the atmospheric pressure. Okay, so in the opened bottle, the carbon dioxide in the soda reaches the equilibrium with the atmospheric pressure. Okay, so what changes is the pressure. Okay, so C is equal to Kp. Okay, so in this case our K remains the same, 3.1 times 10 to the power negative 2 mole per liter atmospheres. Okay, then the atmospheric pressure is 4.0 times 10 to the power negative 4 times 10 to the power negative 4 atm. Okay, then you cancel. So we are going to find 1.2. Okay, 1.2 times 10 to the power negative 5 mole per liter. Okay, so you can see not the large change in concentration of carbon dioxide. Okay, you can see when the bottle is opened, you can see how the concentration has reduced. Okay, so this is why soda goes flat after being opened for a while. Okay, so these are some of the examples of Henry's law. Okay, so application of this Henry's law, it is used for deep sea divers, also mountain climbers. Okay, those who rely on oxygen. You know that at high altitude there is less oxygen at high altitude. Okay, so there are so many applications of Henry's law that you need to look at. So you can do some research on Henry's law applications, you read more. Okay, applications of Henry's law. Okay, you can read more on that. Okay, so now the next topic that we shall look at is the next one that we shall look at in the next lecture is the vapor pressure of solutions. Thank you.